Hello all. In my previous class, I discussed biasing of PN junction, that is forward bias and reverse bias. And also, I discussed IV characteristics of PN junction. Now, in this class, in this lecture, I will start with IV relationship in a PN junction. Okay. See, to compute this IV relationship in a PN junction, first consider the PN junction is in forward bias. Consider the PN junction is in forward bias. In forward bias, actually, what is the total current actually? The total current is nothing but the total current at the junction. The total current at the junction is nothing but sum of whole current and diffusion current. Electron diffusion current. See, this is I total is equal to IPN of 0 and INP of 0. So this is the whole current and this is an electron current. These two are diffusion currents at the junction actually, right? Yeah, first write down. Consider PN junction is in forward bias. Consider PN junction is in forward bias, right? The total current at the junction, in bracket x equal to 0, is the sum of whole and electron diffusion current. Right? That is I total is equal to IPN of 0 plus INP of 0. Right? Yeah. Copy this figure also. Here, let this one consider as equation 1. Yeah, copy. Yeah, next one. See, in case of forward bias condition, actually, okay, the holes are injected from P to N side, right? Then the hole concentration is maximum at the junction. Actually. You know, the whole concentration is moving towards N side, then the whole concentration is gradually decreased. How it is decreased? Exponentially decreased, right? This plot represents concentration versus distance plot in forward bias condition. This is only an N side. Similarly, on P side also is there. Okay. Next, tell me, what is the net hole concentration actually? The net hole concentration is nothing but sum of the net hole concentration. See here, the net hole concentration is represented as P dash of x. We can consider as Pn dash of x is equal to, okay, sum of thermally generated hole concentration plus injected hole concentration. What is thermally generated hole concentration here? Thermally generated hole concentration is nothing but Pn of 0 into e power minus x by Lp. Okay, this is thermally generated hole concentration plus injected hole concentration. What is injected hole concentration? That is Pn naught. Okay, this is our net concentration. This is on N side. Okay, where here what is Lp here? This Lp is nothing but diffusion length of the charge carrier. I think you know diffusion length. Diffusion length is nothing but it is a measure of how much of distance traveled by charge carrier during diffusion process. Okay, write down this. Right down. In forward bias condition, holes are moving from P side to N side. The holes are moving from P side to N side. P side to N side. This injected hole concentration is maximum at the junction. Maximum at the junction. Yeah, underline maximum at the junction, and it is gradually decreases. Yeah, in bracket exponentially. Gradually decreases exponentially, in bracket exponentially, as holes move deeper into N side. As holes move deeper into N side. Therefore, the net hole concentration is given by, write down like this. The net hole concentration is sum of thermally generated hole concentration plus injected hole concentration. That is, write down like this. Write down this equation, that is Pn dash of x is equal to Pn of 0 into e power minus x by Lp plus Pn naught. Yeah, this is thermally generated hole concentration and this is injected hole concentration. Yeah, next point, where Lp is the diffusion length. Yeah. See, consider this one as equation 2. Now, for example, at x equal to 0, see here we are measuring the current at x equal to 0, right? Just consider x equal to 0. Then what is this equation 2 here? Equation 2 is nothing but Pn of 0 is equal to Pn dash of 0 is equal to Pn of 0 plus Pn naught. So from this, what is Pn of 0? Pn of 0 is nothing but Pn dash of 0 minus Pn naught. Now consider this one as equation 3. Yeah, write down. Yeah, copied, right? Yeah. Next, see, for a PN junction, what is the net barrier potential actually? This I already discussed in open circuited condition, right? Already we calculated in my previous lecture. I calculated barrier potential equation, right? See, for PN junction, what is the net barrier potential actually? The net barrier potential is nothing but, so VB equal to VT into ln of PP by PN. This is the net barrier potential equation. See, if the PN junction is forward bias, first open circuited condition we will consider. After that we will consider forward bias. If the PN junction is in open circuited condition, then what is VB here? VB is approximately equal to V0. This V0 is nothing but built-in potential or barrier potential, right? And also, what is this PP here? This PP is equal to PP0, and what is PN here? PN is equal to PN0. Yeah. Yeah, substitute in above equation. Substitute in above. Consider this one as equation 4. Right? Now, substitute this condition equation 4 actually. Then I think this is V0 equal to Vt into ln of, this is Pp0 by Pn0. Right? Yeah, from this expression, what is Pp0 here? So Pp0 is nothing but Pn0 into e power V0 by Vt. Yeah, now consider this one as equation 5. Consider this one as equation 5. Yeah, copy. Yeah, write down this. For PN junction, write down, for PN junction, the net barrier potential is given by, the net barrier potential is given by VB equal to Vt into ln of Pp by Pn. Yeah, consider this one as equation 4. Next point. If the PN junction is in open circuited condition, open circuited means unbiasing condition, then VB is equal to V0 and PP is equal to PP0 and Pn equal to Pn0. Now write down these two equations. Copied, right? Yeah. Next. Next here. See, this time if the PN junction is in forward bias, if the PN junction is in forward bias, what is whole concentration here? I think in case of forward bias, what is VB? Net barrier potential. Net barrier potential is nothing but VB equal to V0 minus V. And what about the PP here? PP is nothing but PP0. And what is here? Pn is nothing but what? Pn of 0. Am I correct or not? What I'm saying here? See, in the previous case, what I consider, in case of, if the PN junction is in open circuited condition, right? In case of PN junction is in open circuited condition, what about the PP? PP is nothing but PP0. And what about PN actually here? In that case, PN is nothing but Pn0. In case of forward bias condition, actually, in case of forward bias condition, what about net barrier? Actually, net barrier is nothing but VB equal to V0 minus V, and PP is nothing but PP0, and Pn is nothing but Pn of 0. Now, in this case, what is the equation actually? Equation is nothing but, see here, this is simply PP0 equal to, this is simply Pn of 0 into e power Vb minus V by Vt, right? This is equation 6. I think previously it is equation 5, right? Now, from equation 5 and 6, right? From equation 5 and 6. So what is that? This is Pn0 into e power V0 by Vt. So which is equal to Pn of 0 into e power V0. Sorry, this is V0. This is V0. Small correction. This is V0. V0 minus V by Vt. Right? Here this and this cancel each other, and what is the expression? Now Pn naught equal to Pn of 0 into e power minus V by Vt, right? Yeah, from this what is Pn of 0 here? The Pn of 0 is nothing but Pn naught into e power V by Vt. Now consider this one as equation 7. This one has equation 7 actually, right? Uh, this is called as law of junction. This equation is called as law of junction. Law of junction. Yeah, copy up to this. Write down. If the PN junction is in forward bias, if the PN junction is in forward bias, if the PN junction is in forward bias, then VB equal to V naught minus V, VB equal to V naught minus V, and PP equal to PP naught, and PN is equal to Pn of 0. Actually, this is Pn dash of 0 here. This one also small correction. Pn dash of 0. Consider this is Pn dash of 0. Yeah. Now, what is an equation here? What is an equation? PP naught equal to Pn dash of 0 into e power V naught minus V by Vt. Yeah. Now from equation 1 and equation 5 and equation 6, now Pn naught into e power V naught by Vt, copy, equal to Pn dash here. Again Pn dash of 0 into e power V naught minus V by Vt. Yeah, copy up to this. This is Pn dash. Yeah, copied now. See, we know what is Pn of 0 actually. Pn of 0 is nothing but Pn dash of 0 minus Pn naught, right? What is Pn dash of 0 actually? Pn dash of 0 is nothing but Pn naught into e power V by Vt minus Pn naught. Am I correct or not? So from this, common the Pn naught here, e power V by Vt minus 1. Now consider this one as equation 8. Consider this one as equation 8. Okay. Now tell me, in case of forward bias condition actually, what is the currents actually? I already told. The total current is nothing but sum of hole and electron diffusion currents, right? Sum of hole and electron diffusion current. Here, first consider hole current density. First consider hole current density at any distance. Hole current density at any distance x is nothing but what? This is Jpn of x is equal to E into dp into dp means diffusion constant, right? dp by dx, right? This dp by dx is nothing but what actually concentration gradient or concentration change. This is minus, right? Yeah, from this what is current actually? From this current is nothing but IPN of x is equal to minus E into dp into A into dp by dx, right? Now consider this one as equation 9. Okay, we know Pn of x is equal to what actually? Pn of x is nothing but what? This is simply Pn of 0 into e power minus x by Lp plus Pn naught, right? Yeah, differentiate this equation with respect to x because we want what actually dp by dx, right? Yeah, differentiate this equation here, then dpn of dpn dash of x dpn by dx is equal to, what is the differentiation of this term actually? This is simply pn of 0 into 1 by minus Lp into e power minus x by Lp. What is the differentiation of this term actually? 0, right? Yeah, copy up to here. Yeah, copied now? Yes. Substitute this dpn by dx in this equation 9. See here. IPn of x is equal to minus E into dp into A. What is differentiation dp by dx actually? Change in concentration. This is nothing but simply Pn of 0, right? So 1 by Lp minus is there, minus minus plus into e power minus x by Lp, minus x by Lp. Okay. Next, here we have to calculate this diffusion current at x equal to 0, right? See, at x equal to 0, what is the diffusion current here? IPN of 0 is nothing but minus E into dp into A into Pn of 0 by Lp. Okay, but actually what is Pn of 0? E into dp into A by Lp. What is Pn of 0 here? Pn of 0 is nothing but Pn naught into e power V by Vt minus 1. Any doubt? Right? And what is this Pn naught? You know that this Pn naught is nothing but Ni square by Nd. Ni square by Nd, that is E into dp into A by Lp. This is Ni square by Nd into e power V by Vt minus 1. I think this is equation 10. This is equation 10. Yeah, similarly, what is the electron current density at x equal to 0 from this expression actually? Similarly, right? Similarly, what is the electron current density here? Electron current density at x equal to 0. That is INP of 0 is nothing but E into, yeah, this is simply dN. Here dp, right? Here dN into A by ln into This is simply Ni square by Na into e power V by Vt minus 1. Now this one is considered as equation 11. Okay. Now tell me, what is our total current actually? The total current is nothing but IPN of 0 plus INP of 0. Yeah. Then what substitute? These two equations, equation 10 and equation 11 actually. Now what is this expression? You know, simply this is E into A into Ni square. Okay. Ni square into dn by ln into Na and dp by lp into nd, right? Nd into e power v by vt minus 1. Minus 1, right? Yeah, copy. Here you can written as similarly electron current density at x equal to 0. Yeah, statement electron current density means whole current, right? Like similarly whole current, na? Electron current density at x equal to 0. Copied, right? Still copying. Yeah, next, listen. Now consider this total one as, this total term can be considered as I naught, right? Now what is the total current here? Now what is the total current? Now I total is equal to I naught into e power v by vt minus 1, right? This is called as what actually? Total current in a PN junction. The total current in a PN junction actually, this is also called as diode current equation. This is also called as diode current equation. So from this, what is I naught here? Where I naught equal to E into A into Ni square, okay, dn by ln into Na, next dp by lp into nd. This is the I naught expression. You know, this I naught is called as what actually? Reverse saturation current. This I naught is called as reverse saturation current. Okay. Next, this equation 1, now you can consider as this is equation 12. This is equation 12. This is equation 13. You know, this equation 12 can satisfy only for germanium diodes. Whatever we derived now, this equation 12 actually it is satisfied only for germanium diode. It is slightly disobeys for silicon diode. That means the theoretical values of germanium and practical values almost same. If we consider silicon diode actually, okay, with this expression, the theoretical and practical will quite means it's having some error actually, right? So means the theoretical and practical values are does not matching. Yeah, to match this or to suppress this error or to minimize this error actually, here we introduce a new term in this equation 1. This new term is called as eta. Here this new term is called as eta. That is I total is equal to what? I total is equal to I naught into e power v by eta into Vt minus 1. Now this can consider as equation 13. Okay, yeah, copy here. Copy. Copy here, you can consider this total term as I naught. Then after that, write down equation 12. Equation 12 and equation 13. Just up to, just you stop here. After that, I will tell you. Up to 13, write down. After that, don't write anything. Just wait. Copied? Yeah. Next one, write down. Equation 12 satisfies only for germanium diode, and slightly disobeys for silicon diode. To eliminate the error between theoretical and practical, a new term is introduced. That new term is called as eta. In bracket ideality factor. That eta is called as ideality factor. That new term is called as ideality factor. Yeah. Next, write down. Equation 12 become. Yeah. Copy this one. Equation 13. Copy equation 13. Right. Yeah. Next one. You know what is the eta value actually? For silicon, actually this eta should be equal to 2. For germanium actually, what is eta here? 1. See, if you substitute eta equal to 1, I think it is equation 12, right? If you substitute eta equal to 2, then I think this is for silicon diode, right? Next, write down. For silicon eta equal to 2, for germanium eta equal to 1. And one more important point actually, whatever the eta values, no, this eta equal to 2 and eta equal to 1, actually this is valid at low currents. At high currents, we are considering equation 12 only. Whatever it is, it's a silicon material or silicon diode or germanium diode, whatever the diode actually, you can consider it. At high currents, when we consider it, this equation 12 only. This is also very important point. Means whatever we are considering eta equal to 2 and eta equal to 1, this is actually at low currents. Means at low current only these differences will occur. At high current there is no problem. Okay, there is no error actually. See, the theoretical values and practical values are matched for silicon if you consider this equation 12. But at low currents, this is quite means it will use some error actually. That's why we are considering this eta equal to 2 and eta equal to 1 like that. Okay, important point here. And next one, calculation of V. V means voltage across the diode. Calculation of V. Next heading, calculation of V. Yeah. Voltage across diode. Yeah, how to calculate actually? We know diode current equation, right? What is diode current equation? I equal to I naught into e power V by eta into Vt minus 1, right? This is the diode current equation, right? So from this expression, what is e power V by eta into Vt minus 1 actually? I by I naught. So from this, what is e power V by eta into Vt, which is equal to simply 1 plus I by I naught. What is V here from this? So V is nothing but eta into Vt ln of 1 plus I by I naught. Now this one considers equation 14, right? Now what is this? See here, this equation is voltage across the diode. And equation 12 and equation 13 is nothing but current to the diode. Okay, copy here. Yeah, next, write in a note. See, for forward bias, consider V and I are positive. Consider V and I are positive. For reverse bias, consider V and I are negative. V and I are negative, right? Yeah, this is all about IV relationship in a diode or PN junction. Okay. Yeah, write in a question here. Write in a question. A germanium diode is operating at room temperature. Write down. A germanium diode is operating at room temperature. A germanium diode is operating at room temperature. Find voltage across the diode. Find voltage across the diode. If the reverse current is equal to 90% of saturated value. 90% of saturated value. 90% of saturated value. Right. Yeah, all of you read the question here once. What is given? Actually, they given a germanium diode. Germanium diode is nothing but what is eta here? 1. Right. Also, what we want to find out here, voltage across the diode, nothing but V. Okay, what is given actually? Reverse current is equal to 90% of the saturated value, right? See here, reverse current is equal to 90% of the saturated, means I equal to 90% of I naught. I already told now this I naught is nothing but reverse saturation current. This I naught is nothing but reverse saturation current. See, whatever we derived a current diode current equation, that equation is valid for both forward bias and reverse bias. You know, in case of forward bias, what is the diode current equation? In case of forward bias, the diode current equation is nothing but I equal to I naught into e power V by Vt minus 1. Yeah, in case of reverse bias, what is the diode current equation? You know, in case of reverse bias, the diode current equation is nothing but I equal to minus I naught into e power minus V by Vt minus 1. This is the diode current equation in case of reverse bias. Just now I told, note, forward bias consider V and I are positive because the characteristics are lies in first coordinate. In case of reverse bias, actually what is V and I? Negative, right? You have to add, right? A negative means I equal to minus I naught e power minus V by Vt. Yeah, that's why for forward bias V and I are positive, for reverse bias negative, V and I are negative, right? Yeah, same way here, means this equation is valid for both the forward bias and reverse bias, but with change of polarities. Now what is given here? Reverse current is equal to 90% of the saturated, right? What is saturated value? I naught. Reverse current is nothing but I, and the saturated current is nothing but I naught. Now, but here we have to add the minus because they given reverse current, right? That's why we have to add the minus. In numericals, they won't give actually, right? We have to add. This is minus 0.9 into I naught. Right, then what is V here? So V is nothing but eta into Vt ln of 1 plus I by I naught. What is eta here? Eta equal to 1. And what is Vt here? Vt is nothing but 26 millivolts ln of 1 plus, this is minus 0.9 I naught by I naught. Now I think this is equal to minus 0.05 volts. See, voltage we got minus because it is in reverse bias. Right, yeah, copy here. Yeah, thank you. To be continued next lecture.